Welcome to the 19th lecture. In this lecture, we will study the empirical rule. In our last lecture, we studied Chebyshev theorem. Chebyshev theorem and empirical rule, they are quite similar to each other. In Chebyshev theorem, we studied that the data distribution is somewhat between k sigma in around the mean with some value of k. A fixed number of observations lie within those defined intervals. But the Chebyshev theorem is based on, or it is valid for any kind of data. But in this lecture, we will study a rule that is not fit for any kind of data, but is only used for the data for which relative frequency histogram is of mound or normal or this bell-shaped curve. So that's the basic difference. The Chebyshev theorem is defined for any kind of data having any kind of relative frequency histogram. But the empirical route that we will study today is meant for the data for which relative frequency histogram or frequency histogram is of normal or mound or bell-shaped. So this is the first thing to know about the empirical rule. And now let's move on and see what this rule says. Right. So for a data set, whether it's a sample or population, but the data should have this mound shape relative frequency histogram. If we work with this interval, the mu plus minus sigma for population and x bar plus minus s for sample, where this x bar or mu is the mu, the center, and sigma is the spread, the standard deviation. So if the data takes on this distribution, so the percentage of measurements that we will get in this interval around one standard deviation from mean, the percentage of measurements will be 68%. If we have 100 measurements, around 68, this is the term is not at least. The term at least, we studied the term at least for Chebyshev's theorem, but here we don't use the term at least. We say around. So that's the basic difference. In Chebyshev's theorem, we use the term at least, but here for this empirical rule, we use the term around or approximately. So in this interval, approximately, we get 68% of measurements. And in this interval, around two means, from mean around two standard deviations, around two standard deviations around mean, we get 95% of measurements, and from mean, around mean, three standard deviations around mean, we get almost 100%, 99.7% observations or measurements. So let's see, or let us try to understand further this empirical rule with the help of an example. Here we have this example. We studied this example once earlier, the lesson plan example, evaluation of lesson plan example. We studied that for Chebyshev's theorem, I guess. I'm not sure, but I guess we studied that for Chebyshev's theorem. Right, but anyways, this is an example of a sample containing 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 25 measurements whose mean is 21.6. The standard deviation is 5.5. So what we're going to do is we want to verify the claims that we have made for using this empirical rule for this bell-shaped data. That is that around mean, one standard deviation around mean, we should get at least 68%. We should get around 68%, not at least, around 68%. So let's see what this interval is. X bar plus minus x. S bar is 21.6, minus s is 16.1, plus s is 27.1. So we get how many we get 16 measurements in this range from 16.1 from 16.1 to 27.1. From 16.1 to 27.1, we get, out of these 25 measurements, we get 16 in this interval. So dividing them by the total number of measurements, 25 times 100 gives us 64%, around 68%. These are a bit lesser than 68%, but they're quite close, 64%. So in this interval, the second interval, x bar plus minus 2s, we get 96%. And the rule says, what does the rule say? The rule says that they should be around 95%. So what we have got, 96%, around 95%, right? And in the interval x bar plus minus 3s, we should get 99.7, but we actually get 100. So let's see why it is approximately, because in this interval we are getting some about 4% lesser observations or 4% lesser measurements than we are expecting. We are expecting around 68%, but we are getting a percentage that is 4% smaller than what we were expecting. The reason for that. Now we are coming to the reason, because there's mound shape, it's bell shaped, it's around bell shaped, it's very close to bell shape. So if we draw, what I'm trying to do is trying to draw an envelope over this histogram. So it's around the bell shape. So it's not exactly the bell shape, but it's around bell shape. So therefore we get this small deviation of 4%. If it is exactly bell shaped, we'll get the results very accurately. So anyhow, it is very close to, I have written it here, near mound or normal. It's also called normal. Mound shaped curve, mound shaped histograms, they're also called normal shaped distributions or normal shaped histogram. So that's all for this lecture, and in the next lecture we'll study more about relative measures in statistics. Thank you.